All right, let's break down one of the most significant shifts happening in EV architecture right now, X-in-1 integration. Look, this isn't just a trend anymore, it's a strategic necessity. But here's the catch, its success hinges entirely on tackling one massive risk, getting functions with different safety levels to play nice on a single chip. And what we're going to show is that the only real bulletproof solution is hardware-enforced isolation.
So here's how we're going to walk through this. We'll start with why this shift is absolutely inevitable. Then we'll dive into the tricky paradox this integration creates and define the huge risk that comes with it. After that, we'll get to the good stuff, the hardware-based solution, and we'll wrap up with a clear, actionable game plan for you to get this done fast.
So, first up, this big shift to X-in-1. Honestly, it's the next logical step in designing a modern vehicle. We're moving away from the old, chaotic world of bolting together dozens of different boxes and into a much smarter, streamlined system architecture.
And this slide just says it all, doesn't it? On the left, you've got the old way, what we call distributed chaos, a tangled mess of individual control units and wires. And on the right, that's where we're all headed, one chip order, where a single, powerful processor runs the whole show. This is a fundamental change from integrating wires to integrating silicon. And look, this isn't some far-off concept. It's happening right now. A market leader like BYD has already rolled out 8-in-1 systems in over half of its new electric vehicles. We're talking mass production, not some science project. And that puts incredible pressure on everybody else to catch up, fast.
So you might be asking, why is everyone racing to do this? Well, the business case is just impossible to argue with. You get huge savings in space and weight, which is everything for vehicle range. You slash your hardware costs by putting everything on just a couple of circuit boards. That makes assembly on the factory floor way more efficient and brings down the total cost of ownership in a big way. These are benefits no automaker can afford to pass up. But, and this is a big but, this physical simplicity creates a whole new world of complexity on the inside. We call it the core integration paradox. The simpler the hardware looks on the outside, the more insanely complex the software and safety challenges become.
Okay, let's look at the first layer of this puzzle, the physical challenges. Yeah, the integrated box is smaller, but it brings two new headaches. First, if one little thing fails, say the onboard charger, you might have to replace the whole, very expensive X-in-1 unit. And second, when you pack all that power into a small space, you create these intense thermal hotspots that need some seriously clever cooling.
You know, the physical stuff, we can engineer our way around that. But the real danger, the thing that keeps engineers up at night, is the logical problem. This is what we call the spark of mixed criticality risk. It's where functions with totally different safety needs and running at totally different speeds are all living on the same piece of silicon. And in that environment, one simple software bug can cause a total system meltdown.
Let's really break that down. Think about it. A single processor has to handle thermal management, a slow and steady task, maybe checking in once a second. That's a non-critical function, but at the exact same time, it's running the inverter control loop every microsecond. That's 1,000,000 times faster, and it's ASIL D, life-critical. So the million-dollar question is, how do you guarantee with 100% certainty that the slow, non-critical task can never, ever mess with the fast, life-critical one?
And that question brings us right to the heart of the matter. We have to be really clear about this risk, because in an X-in-1 system, that one central processor becomes the single point of failure for the entire powertrain. If it goes down, everything goes down.
So here's the textbook definition. Mixed criticality is the challenge of running software with different safety ratings, like your life-critical ASIL D and your non-critical QM on the same chip, without them interfering with each other. A bug in the simple thermal code can't be allowed to crash the supercritical inverter control. That is the problem we have to solve.
And this goal, this absolute necessity, actually has a name: freedom from interference, or FFI. This isn't just a nice feature to have. It is a non-negotiable, mandatory requirement to pass your ISO 2626 safety certification. Getting FFI right is the cornerstone of any X-in-1 system, both technically and legally.
So if a software bug is the potential problem, a software-only fix isn't gonna cut it. The only real solution has to be architectural. It has to be robust, and it has to be based in hardware. We are quite literally talking about building a firewall directly into the silicon.
And this is where a solution like NXP's one-chip control strategy comes into play, with their S32 platform. They have processors like the S32K39 for simpler 3-in-1 setups, and then more powerful chips like the S32K5 for the really complex 8-in-1 systems. The whole architecture is built from the ground up to handle these different levels of integration safely.
So how does it work? Well, the magic ingredient here is something called the XRDC, the Extended Resource Domain Controller. You can think of it as a physical traffic cop or a firewall, right on the chip. It enforces the rules about who gets to access what memory and what peripherals. And it does this at the hardware level. If a non-critical task tries to write to a memory address that's reserved for a critical one, the hardware just says nope and blocks it. End of story.
Okay, let's translate these features into what they actually mean for you and your engineering teams. The XRDC? That's what gives you guaranteed freedom from interference, which is what the safety auditors need to see. Lockstep cores? That's your hardware backup for those critical ASIL-D functions. The CoolFlux DSB? That handles the heavy math so your main cores are free to focus on control. And the software and tools? They make setting up this incredibly complex system way, way easier.
All right, so the tech is there. It works. The next big question is, how do we actually use it without getting bogged down in a multi-year development nightmare? This is where we shift to a practical, accelerated path to get you from concept all the way to production.
The great news is you don't have to start from zero designing a custom board from scratch. You can use modular hardware platforms like this one. It's a motherboard plus daughter card setup. The main board has the S32K39 chip, and then you just plug in different daughter cards for your inverter, your onboard charger, whatever you need. This means you can start testing your software on day one.
And this is huge. The solution isn't just the silicon, it's the whole support system around it. Getting access to pre-certified functional safety concept documents means a ton of the hard safety analysis work has already been done for you. This takes a massive amount of risk off the table and can literally shave months, sometimes even years, off your development time.
So, if we boil this all down, what's our strategic playbook? It comes down to 3 key actions. First, use modular platforms to speed up your prototyping and get rid of early hardware risks. Second, when you're choosing your processor, insist on hardware-enforced isolation. Make it a non-negotiable requirement. And third, plan for the future. Build your software so it can easily move from a 3-in-1 today to an 8-in-1 tomorrow.
And that last point on scalability? It is absolutely critical. This roadmap shows the path from the S32K39 for today's systems to the S32K5 for the next generation. Because they share the same core architecture and software environment, all that time and money you invest in your code is protected. You can migrate it to the next chip with minimal pain.
Okay, so let's wrap this up. What are the big takeaways you need to remember? Number 1, the X-in-1 trend is unstoppable. You have to do it to stay competitive on cost and weight. Number 2, the big safety problem, this mixed criticality risk, is absolutely solvable with hardware isolation like an XRDC. And number 3, you can get there faster than you think by using modular platforms and pre-certified safety docs so you're not starting from scratch.
And that really leaves us with one final, exciting question to think about. Now that we've solved the core safety paradox with hardware isolation, the door is open for innovation. So, what new features, what new vehicle capabilities, what amazing user experiences can we now create and unlock, all because we can finally integrate everything safely?